Invisible rivers of plasma are carving the universe's grandest skeletons right now. And the first stream is something almost nobody guesses, so stay tuned until we reach number 1 to uncover the most unexpected hidden current. Imagine a whisper of ionized hydrogen drifting through the newborn cosmos, a gentle breeze that set the stage for everything that followed. Around 13.8 billion years ago, after the universe cooled enough for atoms to form, this faint stream of primordial gas began to collect in the shallowest potential wells of dark matter. Though almost invisible to early telescopes, its subtle pressure gradients nudged matter together, seeding the first filaments that would later become the scaffolding of the cosmic web. Researchers estimate that this early flow contributed a modest fraction of the total baryonic budget, yet its role was pivotal. Without it, the large-scale structure we observe today would look dramatically different. This quiet current reminds us that even the softest forces can have lasting, universe-shaping consequences.
Surprising to many, most of the universe's missing ordinary matter hides in a diffuse, scorching soup called the warm-hot intergalactic medium, or WIM. As galaxies formed and merged, their gravitational battles heated surrounding gas to temperatures of 10 to 10 Kelvin, turning it into a nearly invisible plasma that threads between clusters. Though difficult to detect, astronomers have traced its faint X-ray emissions and subtle absorption lines, revealing a sprawling network that accounts for roughly half of the universe's baryons. This hot stream acts like a cosmic highway, channeling material into growing superclusters while also cooling slowly, allowing new galaxies to ignite. Its existence solves a long-standing cosmic inventory puzzle and demonstrates how energetic gas flows, far from being chaotic, actually regulate the growth and distribution of the largest structures we see today.
One might picture the universe as a static lattice, yet it pulses with colossal rivers of gas that flow along dark matter filaments, feeding galaxies like tributaries to a grand river system. These filamentary streams, often stretching hundreds of millions of light-years, transport cool, dense gas directly into galactic halos, igniting bursts of star formation. Observations using the Lyman alpha forest have mapped these channels, showing that they deliver a steady supply of fresh material, essential for sustaining star-forming disks over billions of years. Simulations suggest that galaxies positioned at filament intersections, known as nodes, grow faster and become the massive ellipticals dominating clusters. Thus, the seemingly gentle streams of intergalactic gas are in fact the lifelines that sustain the brightest beacons of the cosmos.
Hidden within the outskirts of superclusters are colossal shock fronts that ripple outward like cosmic tsunamis, born when massive structures collide at speeds of thousands of kilometers per second. These shocks compress and heat the intergalactic medium, accelerating particles to near-light speeds, and generating faint radio halos that astronomers can now detect with sensitive arrays. Though the energy involved is staggering, the shocks themselves are thin, spanning only a few 100,000 light-years, yet they influence gas dynamics across millions of light-years. By reheating the surrounding plasma, they can temporarily suppress cooling flows, altering the rate at which galaxies accrete fresh gas. In this way, shockfront cascades act as regulatory mechanisms, ensuring that the growth of the universe's largest structures proceeds in a balanced, if occasionally turbulent, fashion.
Few people know that magnetic fields thread through the vast filaments of the cosmic web, subtly guiding the motion of ionized gas across unimaginable distances. Recent polarization studies have revealed coherent magnetic structures extending over tens of megaparsecs, likely amplified during galaxy mergers and large-scale flows. While these fields are far weaker than those in galaxies, they can influence how gas cools and condenses, affecting star formation efficiency in the filaments they permeate. Moreover, magnetized streams can channel cosmic rays, altering the energy balance of intergalactic space. The discovery of these hidden magnetic threads adds another layer of complexity to our picture of how gas streams sculpt the universe's grandest architecture.
Deep within massive galaxy clusters, infalling gas slams into the hot intercluster medium, creating powerful accretion shocks that glow in X-ray and radio wavelengths. These shocks, often located near the virial radius, act as cosmic brakes, converting kinetic energy into heat and turbulence. By heating the gas, they prevent it from cooling too quickly, thereby moderating the rate at which new stars can form within the cluster's core. Detailed observations with space-based telescopes have measured temperatures soaring above 10 Kelvin, confirming that these accretion fronts are among the most energetic processes in the observable universe. Their role as regulators underscores how gas streams not only build, but also temper the growth of the largest gravitationally bound structures.
Astounding discoveries have shown that, contrary to earlier belief, massive galaxies in the early universe can acquire gas via cold flow streams that pierce hot halos without being heated to extreme temperatures. These narrow, dense streams travel along dark matter filaments, delivering pristine, cool gas directly to galactic centers, fueling rapid starbursts observed at redshifts beyond 6. Simulations suggest that such flows can dominate the mass growth of galaxies up to a critical halo mass, after which hot mode accretion takes over. By bypassing the usual heating phase, cold flows enable the formation of the most massive, luminous galaxies seen in the young cosmos, highlighting a surprising efficiency in how gas streams shape early large-scale structures.
Unexpectedly, the boundaries where fast-moving streams meet slower ambient gas become turbulent mixing layers, stirring the intergalactic medium into a frothy, multi-phase soup. These layers, observed through subtle absorption features, promote the exchange of metals and heat, enriching otherwise pristine regions with elements forged in stars. Turbulent mixing also seeds small-scale density fluctuations that can later collapse into dwarf galaxies or satellite systems. By facilitating chemical homogenization across vast distances, these chaotic interfaces ensure that the fingerprints of stellar evolution are spread throughout the cosmic web, influencing the composition of future generations of galaxies.
Finally, during the epoch of reionization, intense radiation from the first massive stars and quasars drove powerful photon-driven winds that pushed ionized gas outward, carving bubbles that eventually overlapped to reionize the universe. These winds, traveling at several hundred kilometers per second, swept up surrounding neutral hydrogen, creating expanding shells that later merged into the vast ionized regions we detect today. By redistributing gas on intergalactic scales, they not only altered the temperature and ionization state of the early cosmos but also set the initial conditions for later large-scale filament formation. Their legacy persists, as remnants of these ancient outflows can still be traced in the faint absorption signatures of distant quasars.
At last, the modern universe showcases a reinforced cosmic web, where ongoing gas streams continue to feed and reshape the largest structures. Contemporary surveys map the faint filamentary network with unprecedented detail, revealing that even today, streams of warm hot gas flow along dark matter veins, delivering material to galaxy clusters and sustaining their growth. While the overall expansion of space stretches these filaments, gravity and gas dynamics keep them coherent, allowing the universe to maintain its intricate, lace-like appearance. This persistent interplay between invisible currents and massive structures underscores a timeless truth. The universe's grand design is not static, but a living tapestry woven by the ceaseless motion of gas across cosmic epochs.
We've traveled from the faintest primordial breezes to the roaring shock waves that still sculpt the cosmic web, witnessing how delicate gas streams can dictate the destiny of galaxies and clusters. Understanding these flows not only reshapes our view of the universe's architecture but also reminds us how the unseen can dominate the grandest scales. If you enjoyed this journey, subscribe so you never miss the next mind-blowing list we release each week. Which gas stream left you the biggest impression? Let me know in the comments, and if you liked the video, give it a thumbs up, it really helps.